Okay, so in this video clip, we're going to take a look at Cython, and it's a useful extension to the Python environment. It allows us to use C and C++ and compile some of our code. Python generally is we consider it to be an interpreted language. That means it takes a few iterations before it converts to binary code. And as a result can be slower, but not always slower. But in some instances, Python can be a little bit slow. And there may be ways to speed that up if we could leverage a little bit C. So maybe to get some idea here, a little bit more concrete mapping out of what Cython represents. It's a programming language. It's a superset of the Python programming environment. So if A is Python, we consider B to be Cython, right? In other words, it can be used, it can be leveraged within the Python environment, and it's designed to give C-like performance with code that is written mostly in Python with optional additional C-inspired syntax. So the syntax that we get looks very much like C, and that can be set up within the Python environment. And the big advantage of Cython is that we can get the performance of C in some instances and use that within Python. Okay, so in the option pricing area, there's some evidently this can be leveraged, but we're going to take a very simple example. We're just going to take the Black-Scholes model. And generally speaking, we're not going to have issues in terms of speed of estimation in Python. To estimate the Black-Scholes model in Python using any of the standard libraries, performance is going to be fine. And the time it takes to execute a given function it's not going to be a problem. But we'll use Black-Scholes because it's one that's readily available, understood in textbooks, and it does use a number of mathematical operators. And we'll run here first in Cython, and then we'll run using Python without using this compiled language. And then we'll compare the performance. A key thing to note here is that we're using the C-type, C-inspired syntax within the Python environment, and we're reaching C levels of performance. Okay, so the first thing we need to do in the Google Colab environment is load this extension. Otherwise, we won't be able to run Cython code. So we need to run this load ext Cython first of all, and we're connecting to the server, but generally that doesn't take too long. And I have a number of hyperlinks here you might also take a look at. I'll come back, review them a little bit in a moment. Okay, so to run Cython then, before we can run Cython, a little bit like R, we have to put in this double, to run Cython in the Google Colab environment, which is a Jupyter Notebook environment, we have to have this prefix of the double percentage sign and Cython. And then we run, we estimate, instead of saying DEF, which is standard in Python, we use CDF, and we have a C-inspired type syntax, and we return the option price. So if you're familiar with Black-Scholes, this code should be readily understandable. And if not, you can go into Vinegar, Hill Finance Lab, and just go to Black-Scholes. Right, we just go to Black-Scholes, and I have that formula there and so on, right? Okay, so and some interpretation and implementation. Okay, so we've run this code, and note the name of the code. So double is the asset price, the exercise price, double for T, double V is the volatility, the expiration or the maturity on the option, the risk-free rate. We have a dividend here, and then is it a call or is it a put? And we denote that by a +1 or -1. And then we take these relatively standard variables for S, K, T, volatility, risk-free rate, dividend, and then it's a call option. And if we run that, we're invoking this function here, which is Black-Scholes, okay, based in Cython, right? Now, did we run this first of all? Make sure we ran that code. And if it's debugged, it should be fine. And then run this, and it should be fine as well. And we can see it's working. 1045 is correct. And it can compare that against results I've reported in Vinegar Hill. Then, okay, so what we do next then is we take the Black-Scholes model again, and we set it up in pure Python, right? So this is pure Python, and we run it. And again, those variables are the same as before. Obviously, a little bit, the presentation here is a bit different, but it's the same basic formula. We take the same parameter values. Note here, we don't have cy. So this is the Python function coming from here. We run again, okay? And we get 1045, which is the same as 1045 here. And again, we know that that's correct. So both, very good. We get both results that are clear, that both are in line, right? And then we might take a look here at the Black-Scholes Python and run through using this function here, time it. Basically, will perform a number of loops, and then we take the best 3 speeds. Okay, so we run here. So it's really, we run 250 loops. We take the best 3, and we have a 161 US. And we might just go into, for a moment here, seconds, nanoseconds notation. Okay. Okay, so I went on to another website here, checkyourmath.com, and we can see that when we take the results we have here, the U mu S here denotes, we just come down, microseconds, which is equal to 1 millionth. There's a million microseconds in 1 second, right? Okay, so then we fall back and we run the Cython version of this, and we can see here it is 258 nanoseconds. So it's 250 loops, performs that estimation again of the 1045 250 times. Each time it's going to be exactly the same value. But what time it is reporting here is how long did it take for the best 3, right, per loop, right? So for one instance of the estimation, and we're getting here much better performance of 258 nanoseconds. To compare nanoseconds to the microseconds, the nanoseconds is 1 billionth of a second, and the microsecond is 1 millionth. So we're getting 1,000. Once we're in the nanoseconds, the performance is just many multiples better than if we report back in nanoseconds against these microseconds. You can see that the nanoseconds are way smaller than the microseconds. Right. So this is a much faster estimation, and this is, in one sense, one pointer here in terms of how efficient Cython can be relative to regular Python. Now, it's not always going to be. This is not to say that you may not find very efficient ways of running estimations in pure Python, but Cython does open up a C type inspired syntax, and it compiles and has the performance of the C language. And that's something that is can help, can be very important then in the Python environment, where sluggishness sometimes is a problem.